Hello and welcome back. In this lecture, we're going to finish our discussion on the quadratic equations, and the last topic is if we are given a quadratic equation, ax squared plus bx plus c, and let's call it a, right? We want to see how to determine the sign of a for different values of x, for different values of a, okay, of capital for different values of x. Sorry. So if I put x something, what is the sign of a? And we already discussed a specific case when we have two real roots. If the two roots are real, which the condition is delta is greater than 0, and then we realize that if we evaluate a, capital A, at a given number beta, and the sign of a, and compared with the sign of the leading coefficient a, and for the case that it was positive or it was negative, then beta could be between the two roots when it's negative, or beta could be outside the two roots if it's positive, right? But now let's see how we're going to do this. So first of all, we can divide by a, we can factor out a, and then make it a complete square, and we end up with a times x plus b over 2a squared minus delta over 4a squared. Again, this is equivalent to factorization of a times x minus x1, x minus x2, right? And that's how actually we solve the equation. Alright, if so this terms x plus b over 2a squared is always a positive or 0 value, right, for any given x. So this term and this becomes minus delta over 4a squared. Depending on the whether or not delta over 4a squared is greater than x plus b over 2a squared or less than, the whole thing could be positive or negative, right? Negative or positive. And if it's positive, then the sign of capital A, the sign of quadratic equation, is the same as sign of A. And if it's negative, the sign of quadratic equation is opposite the sign of the coefficient A, right? So if delta is negative, we have no real roots, and delta over 4a squared is negative. Therefore, minus delta over 4a squared is guaranteed to be positive, right? And therefore the sign of quadratic equation is guaranteed to be the same as the sign of coefficient a, the leading coefficient or the coefficient of the leading term. Then the expression inside the brackets is always positive, and the sign of a agrees with the sign of x, which is the sign of x squared, right? So if it's delta negative and a is negative, we have the quadratic equation is negative. If delta is negative, we don't have any real roots, and small a is positive, our quadratic equation is positive. Now, graphically speaking, if we have the x and a of x, right? If delta is negative and a is positive, we have a situation like this, right? So our function a of x never crosses the horizontal axis because it doesn't have any real roots. And at very large values of x, a is the same as a small a x squared, so it should go to plus infinity, right? And if delta is negative but a is also negative, then we end up with something like this. This is x, the y-axis is a of x. We end up with something like this. Again, our function, the quadratic function, does not cross the horizontal axis x because it doesn't have any roots, any real roots. So at very large numbers, our function, our quadratic equation goes to negative infinity. Okay? So delta negative, a positive, our function is always positive. Delta negative, a negative, our function is always negative. So basically when delta is negative, we don't have any real roots. The quadratic equation either is always positive or is always negative. There is no change of sign. So no change of sign. So that's very easy to remember in this case. Now if delta is 0, we have two real, we definitely have real roots, but they are identical. Then what happens is that our function actually goes and becomes tangent to the horizontal line. So we our a of x becomes something like this graphically. It just touches the horizon, and this is our double root or identical roots. This is delta 0, but a is positive, and the other case is when delta is 0, we are actually touching the horizontal axis and we have a double root here, and a is negative. So delta 0, a positive, our quadratic function can be positive or 0. Now in this case 0 is allowed because our function is touching the horizontal axis. If delta 0 and a negative, in this case, the second case, then our function is either negative or can be 0 exactly at the root. Okay? So delta negative, delta 0, and obviously you can guess the next case. When delta is positive, then we have two roots. But before we jump to that, let's solve question 55. If b squared is less than ac, then the sine of ax squared plus bx plus c always agrees with what? Okay, let's see. B squared is less than AC. So what is delta? Delta is b squared minus 4ac. So b squared is less than 4ac. So this is less than minus 3ac, right? So if ac is positive, this is actually an interesting question. Let's see. B squared is less than, okay, let's see. If b squared is less than ac, therefore minus ac is greater than minus b squared, right? And therefore minus 4ac is greater than minus 4b squared. And therefore b squared minus 4ac is greater than minus 3b squared, right? And yeah, we made a mistake here. So if b squared is less than ac, therefore minus b squared is greater than minus ac. Therefore minus 4b squared is greater than minus 4ac. And therefore if we add b squared to both sides, minus 3b squared is greater than b squared minus 4ac, right? Because when we multiply by negative sign, the inequality, the direction of the inequality changes, right? And b squared minus 4ac is our delta. So delta is less than minus 3b squared, and this is guaranteed to be a negative number, or 0 if b is 0. But let's assume that b is not 0. Okay? And since delta is negative, the sine of ax squared plus b plus c always agrees with a, right? But here in the choices we don't have a. So the sign of equation agrees with a, but since remember, since b squared is less than ac and b squared is guaranteed to be positive, then AC should be positive, right? And if AC is positive, sine of A is the same as sine of C, right? So instead of saying that, okay, this equation, the sign is always, because delta is negative, the sign is guaranteed to be the same as the sign of A, right? This is general, whether or not there is a relation between A, B, and C, right? But then based on the fact that B squared is less than AC, we conclude that A and C have the same sign, right? Because AC greater than B squared and B squared is positive. So the third choice is the right choice here. Now the final case is when delta is positive, we have two distinct real roots. And again, you can graphically assume what happens. A of x. If I have two roots, x1 and x2, so delta is strictly positive and A is positive. If A is positive at very large values for x, my function goes to plus infinity. And therefore, between the two roots, I end up with a negative. And outside the two roots, I end up with positive. Now, the other case is when delta is strictly positive, but A is negative. Then we have two real roots. We end up with a shape like this. In this case, between the two roots, I end up with positive. Outside the two roots, I end up with negative. So the conclusion here is that between the two roots, the sign of A, sign of quadratic equation, is opposite the sign of A. Capital A times negative. And outside the two roots, we already discussed this, the sign of quadratic equation agrees with the sign of A. A times A is positive. Okay? So the coefficient of the leading term squared determines the sign of A based on the delta. Delta is positive, 0, or negative. Okay? Alright, so based on these facts and the sign of the quadratic equation, we can solve some of the inequalities that involve quadratic equations. So sometimes you can utilize the properties of quadratic equation to solve some simple inequalities. For example, question 56. What is the value of x for x squared minus x plus 12 less than or equal to 0? Again, very simply, this is a quadratic equation. So we can find the roots, or first of all, we can calculate delta or delta prime, which is minus 4 squared minus 12, 4, positive. So we have two real roots, and 6 times 2, obviously that's the factorization. So we have two real roots. Between the two roots, it's opposite the sign of x squared, which is positive. So x should be between 2 and 6, so that we get a negative sign. Okay? Basically, it's this case. Two real roots. The A, the sign of the coefficient of x squared, is positive. So between the two roots, we get negative. At the two roots, we get 0, right? Exactly, get 0. Question 57. Find m such that mx squared minus 2m minus 2x plus 1 is strictly positive. Strictly positive. Again, first, if we want a quadratic equation to be strictly positive, obviously one of the cases is that it should never have a real root, because we don't want it to cross the horizontal axis, right? It's either should be this one, always positive, or always negative. And obviously in this case, we want to be always positive, right? We don't want to cross the horizontal axis. Therefore, it should never have a root. It should not should not have roots, have real roots. Let's just say real roots. Always have two complex roots, but it should never have a real root if we want to be strictly positive. So delta or delta prime should be negative. So delta prime, because there is a factor of 2, is m minus 2 squared minus m. It should be strictly negative. And then if this is the case, the sign of the quadratic equation agrees with the sign of the coefficient of the leading term m. So m should be strictly positive. One condition, and then we want to solve this m squared minus 5m plus 4 is less than 0. And we can easily factor this as m minus 4, m minus 1 less than 0. And m should be between 1 and 4, obviously. Okay? So m between 1 and 4 and m greater than 0. So m between 1 and 4 is the final solution. All right. So quadratic equations are done. So in this book or in this series of lectures, what I've done is that at the end of some chapters, I have a challenge station, which means there are some very, very hard problems that you are encouraged to solve. And what I'm going to do for you, if you don't want to go through them, that's fine. I'm going to post them as a separate lecture, so and go into details of solving them. So this challenge station or stop, it says that we're at the end of quadratic equations. I've arranged a challenge station for you. These problems are kind of difficult. Actually, they're very difficult and complicated. It's really up to you whether to solve them or neglect them. But as always, my advice is solving a few challenging items is better than solving a lot of easy peasy problems. And remember, you have to practice this at least 10 times to really master them. And I'm going to post them in the next lecture.